All right, so chapter 7 is all about the mole, and the mole is one of the most important things we deal with in chemistry. It's kind of our unifying unit that we use pretty much throughout anything in chemistry. And so we're going to talk about the mole, we'll talk about molar mass, and then we will talk about percent composition towards the end. So the mole is kind of chemistry's version of something like a dozen or a ream or a pair. The mole means the same thing to everyone across the world in the chemistry world. And so atoms are so small that the mole is such an incredibly large number. In 1 mole of something, we have 6.022 times 10 to the 23rd items. And now, when I say items, that could be something like atoms, molecules, or what we call formula units. So, that number there, 6.022 times 10 to the 23rd, is on your reference doc for you. But you're probably going to get pretty good at memorizing it because it is so common. So when we deal with the mole, it is really the center of all of our mathematical calculations. If we can get to mole of something, you can get to mole of anything else. And so, in order to go from mathematical calculations of one substance to a completely different substance, you have to get to moles. That's how we get from one substance to another. Um, and then the one thing I want to point out is that you can abbreviate mole, but you can only abbreviate it down to MOL. It does not become a capital M. It does not become a little m. It has to just stay at MOL or MOLE. Those are your only two abbreviations. So why do we care about moles? Well, it's the center of our entire system here. So we're going to learn all of these different calculations in the rest of the semester. But if you take a look, to go from one substance to another, you've got to go to moles. And then to go from grams to maybe the number of atoms, you've got to go to moles. There's no direct correlation without going to moles. So we've got to be able to get there. Now, the first thing you'll notice here is that this might be pretty overwhelming. In chapter 7, you will be dealing mostly with this part here. We're going to be dealing with grams to moles and then all the way down to atoms or ions. We won't get to gases yet. That'll be for our gases chapter. And we won't get to molarity until exam 4. The rest of the exam, other than gases, will be how do we get from one substance to another substance. But right now in this chapter, we're just dealing with one quadrant. We're not going between materials. We're staying with one substance. So, Avogadro's number, what does that tell us? Well, if we had 1 mole of titanium, that means that we would have 6.022 times 10 to the 23rd titanium atoms. If we had 1 mole of oxygen, remember that oxygen is a diatomic element, so it's expressed as O2. If we had 1 mole of oxygen, there's 6.022 times 10 to the 23rd molecules of oxygen, but there's really 1.204 times 10 to the 24 oxygen atoms. And that's because there's 2 oxygen atoms in each oxygen molecule. So we're going to take 2 times Avogadro's number, which is 6.022 times 10 to the 23rd, and we're going to get that number of 1.204 times 10 to the 24th. We can also think about this in the case of ions or atoms. So if we have something like sodium phosphate, Na3PO4, in 1 mole of sodium phosphate, there would be what we call 6.022 times 10 to the 23rd formula units. And you might see me abbreviate formula units as FU. Formula units just means how many of these groupings are there. You could have sodium chloride. You could have barium hydroxide. Anything that is we could have iron oxide. Those are all examples. All of those, if they're ionic, those are what we call our formula units, okay? In a formula unit, you could break it down further, and you could start to go into the different ions themselves. So in 1 mole of sodium phosphate, there are 6.022 times 10 to the 3rd phosphate ions. Remember that a phosphate ion is that PO4, okay? So if you take a look in that formula, you just have one phosphate. So there would be just that 1 times Avogadro's number. If we wanted to figure out sodium ions, what we're going to do is we're going to take a look. Okay, there's 3 sodiums, so 3 times Avogadro's number is going to get us that 1.807 times 10 to the 24th. If we want total ions, okay, there are 4 total ions. There's 4 sodiums, and then there's 1 phosphate ion, okay? So there's 4 of those, and one of those, there's 4 total, there's 3 sodiums, my bad. 3 sodiums and 1 phosphate for a total number of 4. So we're going to take 4 times Avogadro's number to get 2.404 times 10 to the 24th. And then the last one, let's say we want to know the total number of atoms. Atoms is the furthest we can break it down. And so with atoms, we're thinking about all the different ones, okay? You're not thinking about how do they break up positive and then negative. We're thinking about how many are there total. And so for this example, we've got 3 sodiums, 1 phosphorus, and 4 oxygens. So there's 8 total. You take 8 times Avogadro's number, and we're going to get that 4.818 times 10 to the 24th. So you've really got to think about, okay, how can I count in a formula and get what I need? If you think about this oxygen example on the last slide, there are 2 oxygen atoms within a molecule, okay? So Avogadro's number is a conversion factor. We can use this one of 2 ways. If we want to say that we are dealing with a mole, 1 mole of something is always 6.022 times 10 to the 23rd items. And when I say items, I mean atoms for elements, I mean molecules for diatomic elements and covalently bonded things, or formula units, which are ionic compounds. And so for those, if we want to get between, one of those three things, atoms, molecules, or formula units, we're going to use Avogadro's number in 1 mole. We could also use a conversion factor to count atoms within a formula. So in water, H2O, there are 2 atoms of hydrogen. And you can flip that fraction based on how you need it. Again, thinking back to chapter 2, you may have to flip these, or you may have to organize them in certain ways so that we can cancel things on the bottom and be left with things on the top. So, as an example, how many oxygen atoms are in 4.50 moles of sulfuric acid? Well, we are going to start here with the 4.50 moles of sulfuric acid. We'll get into molecules of sulfuric acid, and then we'll get into atoms of oxygen. So we're using 2 different conversion factors here, kind of 3 steps. So we're starting here with what we know. We know we have 4.50 moles. Then, but in 1 mole of sulfuric acid, we know that there's 6.022 times 10 to the 23rd molecules. Okay? So we've gotten out of moles into molecules, and then lastly, we want to get out of molecules and into just atoms of oxygen. So that's where we have to go ahead, count in our formula. There's 4 oxygens in our formula. So we're going to take 4.5 times 6.02 to the 10 to the 23rd times 4. On the bottom here, you can see what I would plug into my calculator. Again, remember that when you have this times 10 to the power, that's where you're going to find that EE button in your calculator. And so you do not want to ever type in times 10 caret. You're always going to just use EE. And so on the rest of these slides, I'll show you how to plug them into your calculator if you got it wrong. So our first practice problem, how many moles of barium carbonate are there if a sample contains 5.00 times 10 to the 25th atoms of oxygen? So this is the same exact problem as the last slide, just in reverse. So here we're going to start with atoms of oxygen. Then we're going to go to formula units of barium carbonate. Formula units, you guys, just means kind of like a molecule of an ionic compound. Barium carbonate is a ionic compound. The term formula unit just kind of means molecule, okay? So don't let that term scare you. Formula unit is just kind of like a molecule. So atoms into formula units, to get there, you need to count, okay? That's a counting one. And then we're going to go from formula units into moles. That's where we're going to use Avogadro's number. All right, if we take a look here, we're starting with atoms of oxygen. And if we take a look, we've got 3 atoms of oxygen in 1 formula unit. Again, formula unit just means if I take a look at that formula, How many oxygens are there? There's 3. So we're out of atoms of oxygen now, and we're left in formula units of barium carbonate. But we don't want to be in there. We want to be in moles. So we're going to get out of formula units into moles by using Avogadro's number there. You can see 6.022 times 10 to the 23rd. And so we get 27.7 moles. How did I get that in my calculator? Well, I took 5.00, then I found that EE button, and then a number 25. Anything on the bottom gets divided, and anything on the top gets multiplied. So we're going to divide by 3, and then again divide by 6.022 times 10 to the 23rd. So the next thing we want to talk about is what's called molar mass. So again, we always need to remember that a mole is equal to 6.022 times 10 to the 23rd items. But a mole of a substance is also equal to its average atomic mass from the periodic table. So in those images on the right side, they all contain 6.022 times 10 to the 23rd atoms of whatever substance it is. But we obtain those masses from the periodic table, okay? So if you look at the periodic table, the molar mass of copper is roughly 63.5 grams. That's what you're seeing there in that image. Tin is 118.7, so that's what we measured out there. So in order to find the molar mass of a substance, you need to go to the periodic table. To find the molar mass as a unit conversion, if we have just a single element, except for the diatomics, the mass on the periodic table is the mass in 1 mole of that element. So any of your non-diatomics, if we're just dealing with one singular element, it's just the mass off the periodic table per 1 mole. Note that you should try to round all masses to the hundredths place. Lead is kind of special. It only gets the tenths place, but almost everything else gets us to the hundredths place, 2 past the decimal. Now, in diatomic molecules, you need to take the mass on the periodic table and multiply it by 2 because you have 2 atoms per molecule. So hydrogen, 1.01 times 2 gets us that 2.02. Something like oxygen would be 16.00 times 2 to get us 32. So that's how you figure out the molar mass of your diatomics. Regular elements, you just take the mass off the periodic table. Diatomics, you just have to multiply it. So what is the mass of 8.00 times 10 to the 23rd atoms of cobalt? Well, here I'm going to start with atoms of cobalt. Then I need to get it out of atoms of cobalt into moles of cobalt, and then out of moles of cobalt and into grams of cobalt. So here we are going to use the first conversion factor of Avogadro's number to get us into moles. And then we're going to get out of moles into grams using the molar mass off the periodic table. So 58.93 came from the periodic table. In my calculator, what I'm going to do is I'm going to take 8.00 times 10 to the 23rd times 58.93 divided by 6.022 e to the 23. Remember that we never want to type in times 10 to the power. You always want to use the EE button. Now, the molar mass of compounds is very similar to the process of diatomics. What I mean by that is you're going to actually have to think about what atoms and how many of them are there in a compound to be able to figure out that mass. So in order to find the molar mass of compounds, what we're going to do is we're going to count the total number of each unique element, okay? Meaning if you've got 3 different elements, you've got to count them up separately. So element A has 1 atom, element B has 1 atom, and element C has 3 atoms, that sort of thing. Then you'll find the mass of each element from the periodic table. Multiply the mass by the number of atoms, and then you'll eventually add all those up. So this is what it looks like. If we wanted to find the mass of sodium carbonate, Na2CO3, what I'm going to do is I'm going to first count them up. I have 2 sodiums, 1 carbon, and 3 oxygens. Then I'm going to head over to the periodic table and find those masses. So sodium's mass is 22.99. I multiply the 2 by the 22.99, and I get 45.98. 1 times 12.01 gets me 12.01, and 3 times 16 gives me 48. Then you need to add all those masses together to get 105.99 grams per mole for this one. And then we would be able to use that molar mass as a conversion. You'd either be able to use it with grams on the top or moles on the top. One of the two. So we're going to continue this previous problem. How many sodium atoms are present in 49 grams of sodium carbonate? So we're going to use our answer here of 105.99 grams per mole to our advantage. We're going to start with grams, then we're going to go to moles using that number that we just dealt with. Then we're going to go from formula, or then we're going to go into formula units using Avogadro's number, and then we've got to just do a little bit of counting. Okay, so we start here with grams, get out of grams and go to moles, then get out of moles and go into formula units. Again, formula units is pretty much the same as a molecule. And then out of formula units and into atoms. So in my calculator here, I multiplied everything on the top divided by everything on the bottom. 49 times 6.022 e to the 23 times 2 divided by 105.99. So I get 5.57 times 10 to the 23rd atoms of sodium. So this one's asking how many molecules of N2O2 are there in 67 grams of N2O2. This is the same process, but just in reverse. Or it's the exact same process. Sorry, not even in reverse. Exact same process. So here we're going to start with grams of N2O2. You need to find the molar mass. Okay, so you're going to have to do a little bit of that multiplying and addition to find the molar mass of N2O2. Then that'll get you out of grams into moles. And then lastly, we're going to get out of moles and into molecules using Avogadro's number. So here is my little addition up top. I've got two nitrogens, so 2 times 14.01 gets me 28.02. 2 oxygens times 16 gives me 32 for a total of 60.02. And then we'll be able to use that as our conversion factor. So it'll get me out of grams of N2O2 into moles of N2O2. And then we'll be able to use Avogadro's number to get us out of moles and into molecules. Okay, so feel free to use that little map that I have to be able to get these conversions. My answer here is 6.72 times 10 to the 23rd molecules. And so how did I get that? I got 67 times 6.022 e to the 23 divided by 60.02. And the last thing in this chapter is percent composition. This tells us the breakdown of the masses of all elements within a compound by percent. So there's two ways that we can do this. We can take a look at the formula, or we can take a look at some experimental data. So for the formula, there are kind of 4 steps, 3 main steps, and the 4th one's a check. So the first step would be to find the total mass of each element using the number of atoms and masses from the periodic table. Just like we did before, where we made that nice list of how many atoms, what are the masses of them, and multiply them together. Make sure you have to do that process and write that all down. Then you need to find the molar mass of the compound by adding all of those numbers from step 1 together. And then the third step would be to take the element masses from step 1, divide it by the total mass of step 2, and multiply it by 100. Repeat that for any or all of the elements that are asked about. And then the last thing would be to check to make sure that you can add all those percents and they get to 100 exactly. You might get to 99.99 or something, but that's pretty close. So here is the percent composition of sulfuric acid. I've got 2 hydrogens, 1 sulfur, and 4 oxygens. I find the molar masses off of the periodic table. I do the math, multiply them together, or multiply the number times the mass. Then I add those all together. I get a total of 98.09 grams per mole. And then to find the percent of each individual element, I'm going to take the masses from up above. The math that I already did is going to lead me directly to percent composition down below. So 2.02 divided by the total mass of 98.09 times 100 gets me to 2.06. Sulfur, I'm going to use the 32.07 divided by 98.09 times 100. And then my oxygen. The biggest mistake I see students make is they use the mass of just 1. You don't want to use the mass of just 1. You always want to use these total masses here. Don't use 1.01. Don't use 32.07 or 16, because those will give you less than small numbers here, and you will not get to 100. Our goal is to get to 100 by adding all our percents. If you don't get to 100, something went wrong. So I want you to calculate the percent composition of each element within calcium hydroxide. So we've got calcium, oxygen, and hydrogen. Calculate the percent composition of each. All right, so here's mass. Calcium, we've got 1, 2 oxygens, and 2 hydrogens because that 2 is outside the parenthesis. So we get a total mass of 74.1. We're going to take the mass of each element. Remember, take those multiplied answers, not just the individual masses. Multiply them by 100, and then you can do your check. If we add them all together, we get to 100 there. The last thing we need to talk about is finding percent composition from data. We're going to find the mass of each component. Usually the mass of one component will be given to us along with a total. And so you're going to take the total minus the mass of one thing to find the mass of the other thing. Then we'll take those masses, divide it by the total mass that's given to us, multiply it by 100, and then we can do a little bit of a check. So this one's a little bit easier. This one here, if I wanted to find the percent composition of 15.00 grams of a hydrogen and oxygen compound, or 0.89 grams of the compound is hydrogen and the remaining is oxygen, this is how I would go and do that. So I know that my mass of my hydrogen is 0.89 grams. I need to find the mass of my oxygen, so I'm going to take my total mass minus hydrogen, and so I get 14.11 grams. And then here, you're going to take those exact masses that we just found and divide it by the total mass. So 0.89 divided by 15, and then 14.11 divided by 15, multiplying those by 100, and we get 5.9% hydrogen and 94.1% oxygen. We add those together, we get 100%. So what is the percent composition of an iron oxide compound where 7.98 grams of a 26.55 total sample is oxygen, and then the remainder would be iron? So here this is saying 7.98 grams is oxygen. The total sample is 26.55 grams. You're trying to find the percent of oxygen and iron. So here's our answer. We know the mass of oxygen. We're trying to find the mass of iron. So we take the total minus the mass of oxygen. Then we're going to take each of those masses, divide by the total mass times 100. So about 30% of our compound is oxygen and around 70% is iron.